Let's now take a look at factorising when we've got rational or variable exponents. So let's say we've got an example of 5 to the power of x plus 2, and we're adding 5 to the power of x. And we want to factorise this, which means that we want to put it back into the brackets. Well, to do something like that, I want to actually factorise this by taking out the highest common factor. But to be able to take the highest common factor out, I actually need to use an index law. And the index law that I'm going to use is when we're adding these exponents here. Now, when we're adding these exponents, if we work backwards, what that actually meant is we had a situation where we had two bases that were the same, but they were multiplying with each other. So our base in this case is 5. So if we had 5 to the power of x and we multiplied that with 5 to the power of 2, this would simplify back to keeping the base the same but adding the exponents. So that is the same as that. Now, of course, we've still got to add our 5 to the power of x afterwards. But what I can now see here is both of these terms have a common factor, and that common factor is 5 to the power of x. So I can remove 5 to the power of x out of both of these, which will leave me with 5 squared, which is 25. And 5 to the power of x divided by 5 to the power of x will just be 1. So it'll be 25 plus 1. Now 25 plus 1 is going to be 26. So this will simplify, and I'm just going to bring it to the front, to 26 times 5 to the power of x. Now, this here captures the basic principles that we're going to be using when we're factorising here. Is we're going to be looking at these terms individually and going, can I apply an index law to be able to break that term up and then factorise it from there? So another example of that might be if I've got 5 to the power of x plus 2 and I add 50 at the end, and I want to go about factorising this. Well, if we break this up the same that we did before, we know that this 5 to the power of x plus 2 is the same as 5 to the power of x multiplied by 5 to the power of 2. And then, of course, we can add 50 here. Now, this here, 5 to the power of 2 is 25, so this will be 25 multiplied by 5 to the power of x plus 50. And now I want to look at a common factor between here, and the common factor here is 25. 25 divides into both terms. So if I take the common factor of 25 out, it leaves me with 5 to the power of x, and then 50 divided by 25 is 2, so we plus 2 here. And I've now successfully factorised by removing a common factor of 25 out of both terms here. But let's take a look at one more. Let's say we've got two terms where there's a variable in both, similar to what we had at the top. So let's say we had 5 to the power of 5x, except this time we were adding 5 to the power of 3x. Now, when I've got a situation like this, because I've got 5 to the power of 5x and 5 to the power of 3x, I know that both of these terms have at least 5 to the power of 3x in them. So I need to break up this first term, once again by using that index law of when you're multiplying two terms with the same base, you keep the same base, but you add the exponents. So keeping that in mind, if I'm breaking this one up, I want to break it up to have 5 to the power of 3x. And I want to multiply that with something with the same base, so 5, but I need to add on another 2x to get to my 5x. So it needs to have a power of 2x, and that will simplify back into here. Now, of course, I still need to add on my 5 to the power of 3x at the end, and I can now see here that I've got two terms that have a common factor of 5 to the power of 3x that I can remove. So if I remove that, this will be 5 to the power of 3x. What I'll be left with the first term is my 5 to the power of 2x. And on the second term, I'm dividing it by itself, so it'll be just 1. So I'll add 1 at the end here. And now I've factorised this by removing the common factor of 5 to the power of 3x.